Now we're going to look at what can happen as you start to add more and more features into your model, in particular where we run into issues of overfitting. So we're going to actually work with a data set here of some information about cars. It's different than the hybrid data set we had been working with. Now we're going to look at a data set where we're going to try to model miles per gallon as our output. And one of the predictors we can use is horsepower. So if I just try to do a basic linear fit, I can see visually this is not great. My mean squared error ends up being right around 24. And so in order to capture this nonlinear relationship that we can eyeball, like I can see that I have more of a nonlinear curve like this happening here, we could try to add a nonlinear feature. So let's go to the notebook and do this. So we are in the modeling folder, linear regression subfolder, and now in a new notebook called cross-val. So let's go ahead and run the first few cells here and we'll load in our data. There's actually, Seaborn has some built-in data sets, and here's one of them that describes fuel mileage measured in miles per gallon of various cars and along with other characteristics. So you can see a snapshot here of what this data set looks like. So suppose we want to try to predict miles per gallon using these other features. And let's start with the simple model I showed in the slides where we're just going to use horsepower. And here, if I do this, we got this model that we saw with our mean squared error just around 24. So now if I want to capture that nonlinear relationship, one way is I can start to add higher powers of horsepower. So in this example, let's do that here. The only thing that's changing, right, is that now I am adding a term or a column here called HP squared. And now I'm going to refit the model with that new design matrix X here. So everything else is the same. And if I run this, now we can see, okay, my mean squared error went down. This looks a lot better, right? Now it's like 18.9. But then you could think, well, what if I added another term? What if we allow this, to have higher order polynomial? And so what I'm going to do now is look at third order and fourth order and fit those two models, and then we'll plot them. So I'm skimming over the code here because what's more important is this visual as well as comparing the mean squared errors. And so you can see I keep getting my mean squared errors to decrease. And then you could think, well, why stop here? Oh, and I'm going to put these side by side here. Okay, great. But why stop here? Like, why not keep going, really? Because my mean squared error is decreasing. And so what I want you to realize is a couple things. I'm going to just scroll down. Again, the code in this, I don't want you to get too caught up. I'm using a feature of Python called pipelines, and that is out of the scope of this course. This, and same thing with this polynomial features, both of these code pieces you're welcome to look into, but they're really just for ease in quickly creating the plots I want to create. They're not really in the scope of what you need here. I just want you to understand the theory behind them. But I am now plotting, let me do it here. There you go. That's what you can see better. I'm adding more and more powers of horsepower, and I can see that like I keep getting my mean squared error basically to decrease. And this is a plot of my training mean squared error. I'm calling training because we're looking at the data set and we're training the model on the data set. And I can see it just keeps basically decreasing. I mean, it kind of plateaus, but it's still going down. So my question is, when do I stop, right? And I want you to think about the math underneath this. It's actually a mathematical fact that if you create a polynomial model with degree n minus 1, so here I'm going to just do that randomly, again, just so you can see pictures, I can perfectly model a set of n points. So for example, a set of 5 points can be perfectly modeled by a fourth degree polynomial, and that's what I'm showing you here. That's assuming that those points have a functional relationship with the inputs, right? So I don't have things where my points are the same input has two different outputs. That wouldn't be modeled by a function perfectly. But in these cases, right, I can get perfect fits. And so it can be tempting to say, oh, well, let's just add the highest polynomial degree that I can to get my mean squared error as low as possible. But what we're forgetting is what we're creating these models for, right? So typically, I'm trying to create a model using some data to predict what's going to happen with some unknown data, right? Or to predict what's going to happen with some future data. I'm not using the entire data set from the whole population to create my model. So what we've been looking at so far to create our models is basically an artificial scenario. We're training our model on all the data we have available and then using it to make predictions on the same data set. This is not realistic. What we normally end up doing is try to apply our model on unseen data. So let's pop back over to the slides here so that you can see the issue with basically trying to overfit and perfectly fit our training data set. So I'm going to just show a visual of what we saw in the notebook, right? This is what we saw as we increased the degree of our polynomial, that our mean squared error on the data set we were training everything seemed to decrease. And on the right, I have a schematic to represent this idea. And really, I'm going to put in a few terms we're going to start using throughout the rest of these lessons. So the first is we're putting error here, which is my mean squared error, or your root mean squared error, but here I'll just be using my mean squared error. And then model complexity. So in that case, for this example, the higher order degree that we're using, the more complex the model. So you could imagine, right, if we just stopped after a second order model, that's not as complex as if we allow it to go out to like the 5th or the 8th power. And the training error that you see here is basically exactly a schematic of this curve, right? It's just a more idealized version. But in general trend is your training error is going to decrease as you give your model more information to try to use to fit the data. Okay, so why is this a problem? Okay, so this is exactly what we showed in the slides, right? Is that I can get perfect polynomial fits. And again, this should look like, wow, this is great. Why is this the problem again? Well, let's think of the fact that we're training our model on a sample. And then we're trying to use it to make predictions on data that it hasn't seen. And so let's actually simulate this idea where we just take a sample. And so I'm going to just do this with 6 data points, right? Just a random sample of 6 and train the model on those 6. So here's one random sample of 6 data points. And this is a model that perfectly passes through every data point. So my mean squared error for this model would be 0 because I'm able to exactly predict each of these data points. But in reality, this was the data set that I sampled those 6 points from. And so I've really missed the overall trend in this data by overfitting. This is what we mean by overfitting. I worry so much, I zoom in so much on the sample data and try to get that working that I lose sight of the overall trend that may be happening in the data. So what went wrong? Again, I created a really complex model, and that complex model worked perfectly for those 6 sample data points, but was horrible when I tried to use it to predict any other points in this data set. And this is the idea of overfitting that we want to account for when we're creating our models. We want to not overfit our models. So we have a couple terms. I'm going to just define this visually today, but in our future video, when we talk about the bias variance trade-off, I will actually explain this mathematically. But we have the idea of what's called the variance of a model. And visually, what I like you to think of that as is if I take random samples, right, and fit the model to those random samples, if the models that result, so in this case the red curves here, here, and here, if they look wildly different, then this is an example of high model variance, right? My model is really sensitive to the actual sample data points that I choose. And ideally, we don't want high model variance because that means we're just basically fitting what we're going to call noise. We're like overly zoomed in on the sample and not looking back at the big picture. So we can add this idea of variance, and I'm just going to do it schematically here. And then, like I said, we'll do this mathematically in a future video. The dilemma is that we can usually decrease our training error by making our model more complex, adding more features, adding higher order terms. But as soon as they get too complex, they're going to start to overfit, and we're going to increase. We're going to have high variance in our models, which means they're not going to be useful when I apply them to data I haven't seen. And so this is just a schematic of a way of visualizing this. The error here is in blue, and again, we can measure that with mean squared error on our training data set. Variance, now I will show you mathematically there is a way to measure it, but visually I just want you to picture it as, how different are my models going to behave as I provide a different sample sets. And so we really want to try to find the sweet spot. That's the idea of not overfitting, is trying to find this point at which, our training error is pretty low, but we haven't missed the key trends in the data and we haven't overfit. So that is the goal of the next few lessons.